And we're on the air. Hi, everyone. This is another episode of Absolute Zero. I'm Bertrand.
I'm Rachel.
And today we are talking about distances,
How far
cosmic
away
distances.
it is, yeah.
Yeah, how far away it is.
How
Because
far away it is. So
um,
scientists, how do they know how far away things are since we do not have gigantic measuring tapes?
did anybody try that, to just...
I have. I tell
You
you, did
have?
not end well.
How far did you go?
Tape measure only goes so far. That's really
Yeah.
difficult.
Maybe if you tape a tape measure
Keep
at the end
taping
of
it.
another tape measure. Yeah, so that is a problem actually. How do we know that this star is 4 light years away or 1,000 light years away and so on?
Right.
So on Earth, it's easy to measure things because, yeah, tape measures.
Yes. Well, there's also a
Or,
limited amount of measuring that you can do. Right? The Earth is only so big. Right?
yeah,
Once you get out into
but
space,
even on the Earth, measuring stuff is not that
it's
easy.
not that easy. No.
Necessarily.
Yeah.
Um, you need to, yeah, what is a measurement? It's comparing something with something else, right? So with some kind of reference. And for the longest time, we've used, so people in France at least have been using the standard meter, which is a
That's a
bar of
metric
metal.
system.
Do
What is
do
that
you know
silly
about
stuff?
the standard meter, how it used to be defined?
No,
So
maybe.
it was a bar of metal that was kept in
Oh,
very strict conditions of humidity, temperature, and so on, so that the size of your reference doesn't vary too much. Because if your reference varies, then your
right.
your measurements are going to vary with them, and that's not very accurate. And that's true of everything we're going to say. So there is an uncertainty that is associated with any measurement that you do, whether it's distance or something else, and that is super important to understand,
Yep.
um, especially when we talk about um, very long distances.
Time or weight, any of it.
What?
Distance and time, especially.
Yeah, uh,
Measuring those. Yeah.
yeah. So there is that. So there is this uncertainty, and to always understand that you are actually making comparisons. You're not measuring something. I mean, yeah, it's a comparison. It's not absolute. You're comparing with something else.
Right.
Um, so the variations of that standard meter, of course, wasn't exactly desirable. So we had to find something better if we wanted to measure stuff that varies with values that are smaller than that uncertainty that is inherent to what you're using to measure. So if you want to measure something that is smaller than the precision of your instrument, you're in trouble,
Yep.
right? Um, so nowadays, we define the meter in terms of wavelength, I think. So we compare with light or at least electromagnetic radiation that is emitted from some standard events, such as what a specific atom at a certain temperature will emit. So you control that, and you look at those very specific wavelengths that are emitted by some atoms, and that gives you a standard distance.
Very precise.
Yeah, which is much more precise than what we were doing with the standard meter before. And I believe we do the same thing with time. We also measure time by comparing it with some
Atomic clock.
very precise atomic transitions.
Yep.
So
So
that's, yeah.
I know that what astronomers also do with that. So I have all these caveats around measurements, but they'll take a look at stars and they'll see other objects that are orbiting around them, and they could tell by how bright they are, how far away they are. And they found out that the different types of stars, like you have the blue, the red giants, and
Yeah.
various different types, they emit different types of light. So that
Yeah.
becomes
So
contrast
so
or not.
we're
That's how
going
they
to look at the
eventually.
details
Yep.
of that, but those methods haven't been available for that long actually. And you know, for people our ages, it's hard to imagine that even a century ago, galaxies weren't something that people were very familiar with.
Right.
Uh, 2 centuries ago, people had no idea that there were galaxies.
Right. Right.
Um, we had these fuzzy objects in the sky, but nobody knew what they were in reality. But we've been measuring the distance of stars for about 200 years. And the first method that's been used to start to measure the distance of stars is parallax methods. So parallax methods are kind of interesting, and today we have drawings.
Ooh. Okay.
Yeah, fancy. Huh?
Yeah, because the parallax stuff is about like angles and
Exactly.
maps
Yes.
and all that. So this would be really good for nice.
Yeah. So you have a star here that is not too far away, because if it's too far away, that won't work, and we'll see why. And here you have the sun.
So I can still
Okay.
see you. Should I see the whiteboard here?
You should see the whiteboard. Yeah. I should be sharing, so maybe I'm not. Present to everyone. I think I have to do that, and that's
That's good.
unfortunate. Can see it now? Okay.
Yep.
And you have the orbit of the Earth. So here you have the Earth. It looks exactly like that. And of course, the Earth is bigger than the Sun. You just look in the sky, you'll see.
Throw on the scale.
Okay. So what counts is not my crappy drawing. What counts is the distances we have here. Okay. So the distance that we're trying to measure is this one. We know this distance here. Should we talk about how we know this one?
Yes. How do we know? How do we know that one to begin with? Are we just making shit up? Is that it?
Okay, we'll get back to that one, but
Okay.
let's assume that we know this one already, by all means. Okay, and then we have this angle here. And the way we know this angle is because, let's say we're in summer here, and the Earth moves during the year and arrives here on the other side of the sun.
Pretty sketchy path right there, but
Yeah, you know the Earth wobbles a bit because of other planets. This is why I drew it this way. Okay, so this is winter.
okay.
So here, when you look in the sky, so you have other stars in the sky, right? You have some that are very, very far away.
Yep.
And you notice that when you're in summer and you look at this particular star, and you're in winter and you look at this same particular star, it moved. Not by a lot, just by a tiny fraction of a minute of angle. Because when we look at the position of stars, we're actually talking about angles. It's the angle at
Right.
which you look, okay? So it moved, but by a very, very, very tiny amount. And it's only in 1838 or something that this was actually measured for the first time. And from this angle here, so the difference in positions is the difference in angle, because if you take that line here and you draw the same line here, you can see that this angle and this angle are the same.
Mm-hmm.
Okay. And this one here is half of this angle here. Okay. And do you remember trigonometry?
No.
Okay, so this distance here, it's one astronomical unit, which is the standard way we define the distance between the Earth and the Sun. And okay, so the tangent of that angle, alpha over 2, is A over D. Okay? And that means that you can calculate the distance here as A over the tangent of alpha over 2. Okay, so we have a formula that we can apply. If we know A and we measure alpha, then we have D. And well, you can simplify this a little bit. You can know that when alpha is small, which is the case here, it's very, very small, you can approximate this tangent of alpha over 2 as alpha over 2. So that's A over alpha over 2, and that gives you 2A over alpha. So that's a very simple formula that you can apply. And if you do that, and with the precision that we had 2 centuries ago, you can determine the distance of stars that are a few light years away.
Yeah, and that's another thing about these distances, right? Different, kind of like we talked about the radio dating, right? Different methods we use to measure different ranges of distance.
Yeah.
So a few light years away, we might use this one.
Yeah,
and there's
and
methods for things that are further away.
And what we'll see as we describe the other methods that are available, we see how we always have more than one way of determining the distance of some objects. So we have some corroboration between those methods, and that gives us confidence that we can apply the method in other cases where we have only one way of knowing.
Right.
And this is how we propagate our ways of measuring distance from one method to the other, and how we go farther and farther away.
Yep.
So of course the uncertainty usually becomes larger and larger as you go farther away, because we are actually compounding the uncertainties of the various methods that we used along the way. But this is completely accounted for. We know those. We know how to evaluate them. So.
Right. We know what the error bars are, and yeah, once you're talking about these kind of distances between galaxies, what's a few 100,000 miles?
Yeah, and we're usually talking about uncertainties around 10% or 5%, which might seem like a lot, but it's enough to give you a good confidence about the ballpark estimate of the distance of those objects.
All right, so that's one of the earlier methods, and then I think Doppler shift came after that, right? They started measuring that way for a while?
Yeah. So I think we should talk about Doppler shift last, because that's actually the one we're going to use for the farthest of objects.
Okay, yeah, sure.
So parallax is still in use today. We're still using that, and what improved since the 19th century is that we're able to measure angles with much better precision now.
Right.
So the precision that they had at the time was about 1/3 of an arcsecond. An arcsecond being, so a second is a 60th of a minute, and a minute is a 60th of a degree.
Okay. Yep.
And the degree, you know what this is. I mean, there are 360 degrees for a whole term. So we're talking about really small angles. But now we can do. So there is a new satellite that was launched in 2010 that's called Gaia, and that one can measure 100 micro arcseconds. So we are talking about millions of degrees. So that's very impressive, and that enables us to measure the distance of stars that are up to 30,000 light years. So pretty much anything in the galaxy, I think.
That's pretty darn far. So the light year being as fast as light can travel in one Earth year, right, through the vacuum of space, which is pretty damn far. What is it, like 100 trillion kilometers or some crap like that?
Uh,
It's like a ridiculous amount of distance.
let's look at the
Oh,
exact.
if only we had like a library that we could look these things up with our
Yeah, if
computer.
only there was a website that could give you
That wouldn't
answers
help us with
to
this.
what is a light year. So a light year is the distance that light travels in a year in a vacuum, and that is 6 trillion miles.
Yeah, pretty far.
Yep, it is. And the closest star is about 4 light years away.
So pretty far. And that
Pretty
would
far
be
as well.
our star.
What?
Would that be our star, right? The closest one.
Yeah. Uh, so how large is the galaxy? We can ask Google that. And um, our galaxy is 100,000 light years in diameter. So I was saying that we could do 30,000 light years. So that's not exactly the whole galaxy, but we can measure the distance of most things in the galaxy.
So I think you saw the recent news then about Stephen Hawking and a few of, I think, Russians got together and they're going to put out like a new kind of space. Uh,
Yeah, so they want to build a very lightweight probe that can be pushed by light.
and over the next 30 years or so to hit another galaxy, which
No, no,
kind of
no, no,
ridiculous.
no, no, not galaxy. No,
I don't know.
another star. They want to go to.
All right, another star. All right,
Yeah.
good enough. Close enough
No.
for me. Like to be impressive, close enough. That's what I mean by close enough.
Yeah.
Impressive either way, right? That we could do.
Yeah. So the next method that we have after there is another method that is actually pretty close. That's called long baseline interferometry. So this one doesn't use the distance between the both ends of the orbit of the Earth. It actually can work just on the Earth by having two radio observatories on two sides of the planet.
Okay.
And the idea with this is to use interferometry
Okay.
with radio waves. So it's a planet-wide interferometer.
Okay.
And what interferometers do is that they combine light coming from the same object or radio waves coming from the same object, but on different angles, and they combine that and get interference patterns.
Interesting.
Because the light or radio waves that travel in one direction will have to go more distance than the light going from another angle. Okay. If the object is here,
do they do this with
this
only
distance here is larger than
points?
this distance here. Okay.
Yeah. Do they do it with only 2 points on Earth, or do they do this with multiple?
No. You do it with more than that. I'm just simplifying.
Okay.
Then you combine the light or the radio waves from these 2 points, and depending on where the wave is, if it's on top or on the bottom, they can combine and cancel themselves or reinforce themselves. Okay, so on some places you will get a reinforcement and you'll get a bright spot, and on in some places you will get a dark spot.
Okay.
And by looking at the pattern of those light and dark spots, you can determine in which direction the object was, and that gives you a very, very precise measurement of that direction. And that direction is that angle that we've been talking about from the start. And because this is a lot more precise than just looking and measuring, this enables us to measure distances up to 8,000 light years, just using the interferometers on Earth. So we don't have to go into, we don't have to use satellites for that. So that is another method that we use to determine the same distances. So one thing that I learned while reading that, I had never really wondered about that. Do you know what the definition of a parsec is?
Mm-hmm.
So parsec is a unit that is often used for the distance of objects in the sky, and it comes. So the part of parsec comes from parallax.
Oh, geez.
And sec is
Well,
second.
now that you say it, it makes a lot
Yeah,
of
parallax second, parsec.
Yeah, okay.
So a parsec
obvious
is the
now.
distance of an object that gives a 1 degree difference of parallax on the Earth orbit. So if you make the calculation, that's about 3 light years away. So a parsec is about 3 light years. Yeah, so the first one you mentioned was using the light that the stars emit, so the spectrum of a star. So that one is kind of interesting because it tells you a lot about stars, and it kind of depends on some of the knowledge that we have of how stars work and how stars evolve and change over time. Basically, the idea is that there is a way that you can relate the type of star with its brightness, because here we're trying to determine a distance, okay?
Yep.
So we have a bright object, and the farther it is, the fainter it will become,
right?
Obviously. And the relationship between the intrinsic brightness of the object and the distance is that if you're twice farther, then well, it varies with the inverse square of the distance. So if it's twice farther away, then it will be 1/4 of the brightness.
Right. Now, should we go as far as to explain, like, well, how do they classify stars, or should we just say, look, they just classify
well,
stars?
actually, we don't really need to, because it's more like an observation.
Really play into the measurements, other than saying that this is already.
Yeah. So so the way you determine what type of star is by looking at its spectrum. You see what type of light it emits, what the different wavelengths are, and from that you can determine if it's burning hydrogen mostly, or if it's burning mostly lithium, and so on. And you can determine where it is on the classification of stars that we have. That depends on their size, on their age, and so on. And there is a subcategory of all that, which is called the main sequence of star evolution. So it's those stars that are not dwarfs, that are not giants, but that are they are medium stars that are on their regular evolution. So we know how to recognize those stars, and the nice thing about those is that there is a relationship between their brightness and their type, which enables us to determine their absolute brightness, and from that we look at their observed brightness, and from that we derive the distance from that inverse square relation. And this is not just, we know that both because we know quite a lot about how stars evolve and work internally, and also from empirical observation, because some of those stars are close enough. A lot of those stars are close enough now that we can use parallax to determine their distance. So we can corroborate this, and we can establish that relationship empirically without necessarily having to know how they work.
Right.
But it confirms everything we're saying. So that's another way we we determine the distance of stars. And then after that, we have to use standard candles. And standard candles are objects that we know the brightness of for other reasons. So there are mainly two types that we are using. You have Cepheids, which are periodical stars. They are variable stars. And there is a relationship between the frequency at which they change and their brightness.
Okay.
And we know that, again, because we have observed some that are close enough to be investigating using parallax, and also from models of their evolution. But those are not the most interesting ones. The most interesting ones are supernova.
Yeah.
Because that enables us to measure the distance of galaxies.
Right.
So it doesn't work with all types of supernovas. Supernovae. You need to use type 2, a type 2 supernova, which is an explosion that happens in a binary star system where one star is eating the other, and when that happens, so the gas from one star falls onto the other star, okay? And there is a certain limit to that, after which it starts to collapse because it's becoming too heavy to sustain all that extra gas that's arriving. And the result of that is that carbon starts to the fusion reaction, and this is a very sudden phenomenon.
I was going to say this sounds sudden and violent.
Yes,
Yeah.
it's extremely violent. It's one of the most violent events in the universe, and as a side note, this is where most of the heavy elements that we have in the universe actually come from. It's from that very violent event. And what happens is that so a lot of new elements are created during that, and some of those are very radioactive, very unstable, and they start decaying. And they start decaying exponentially, like all radioactive decay does. And the rate at which those elements decay depends directly on the brightness of the object, of the supernova. So that gives us, so by looking at so we're observing, when we spot a supernova, we observe how fast the brightness is decreasing after the event. And from the shape of from the rate, how fast it goes, we can determine how bright it was. And that gives us a standard candle. And we can determine the distance from that.
A lot of work.
Yeah, yeah, and a lot of ingenuity, and a lot of, it's very, yeah, lots of those are really smart, and you can see that it's a hard problem that was solved in very creative ways.
Right.
And the last one is the cosmological redshift. So what do you know about this one?
Well, from what I remember from this one, it's not like I work in this field or anything, but basically so you have like the Doppler effect. As like sound or light comes near you, you see it at an intensity or hear it at an intensity, and then as it goes past you, it's a different intensity, right? So it may become more intense as it nears you, and then less intense as it goes away from you. So both light and sound you can measure that way, right? So that's kind of what they're doing with that.
So the Doppler effect gives you the speed of an object. It doesn't give you its distance, right?
Right, right.
Um, so
But
we
you can
do
measure the
use.
light in a similar, conceptually a similar
Yeah, so
fashion as
it works
light.
for light exactly the
Yeah.
same way, and we actually use we use that to determine. Oh yeah, that's one that we actually haven't mentioned. This is interesting. So when an object is going away, the frequency of whatever it emits is going
Right.
down, and when it comes towards you, the frequency goes up. So high pitch when it comes, and low pitch when it goes.
Right.
And so if you observe a star that is, for example, rotating around a black hole at the center of our galaxy, you can you can look at the difference in the light that's coming from that star
Right.
between one end of its rotation and the other,
And the other.
and that gives you its speed. And if you know its speed from basic mechanics, from Newton's laws, you can determine the size of the orbit. So that gives you another distance, which is the size of the center of the galaxy. And from that, you can infer a lot of other distances. So that's an interesting one. So we are using the Doppler effect to determine distances. But when we talk about cosmological redshift, that is actually something a little different that's happening. So what causes the cosmological redshift is that the universe is in expansion. So that is space itself that is expanding.
Right.
So you have some light that is being emitted by a star, and over billions of years, it's going to travel and reach us.
Right.
And in the meantime, the space between the object that emitted the light and us has inflated.
Yes. It's going to be longer than what we thought we were looking at.
So the distance that the light had to travel is actually something different from the distance that the object is, really, because it actually expanded in the meantime. And it's different from the distance the object was when the light was emitted.
Yep.
So all those distances are different, and we have to agree, well, which one are we exactly measuring?
Right. So which one are they measuring?
So the one that you are actually measuring usually is the distance that the light traveled, which is different from the two other distances that I mentioned. So you're not actually measuring the distance from that the object was really, and you would have to say when.
Exactly.
So it's not an easy problem, but the thing is that the light was also stretched with space.
Oh, so now that's where it starts getting all weird when you talk about the light getting stretched with space.
Yes.
It's one thing like you think about objects that are out that far. By the time you even see the light, even from the sun, it's like 8 minutes ago, right? So you're actually looking at something that happened 8 minutes ago. It's light from the sun, right? So these objects are, greater distance, so it's the same thing. But now you're talking about light gets stretched on the way. I didn't actually even know that.
Yeah, so the cosmic expansion means that light gets stretched as well and seems to lose energy.
Interesting.
Because what happens when you stretch the wavelength of a wave?
Yeah, yeah.
The frequency becomes lower.
Yeah, interesting.
And because the energy of a wave depends on the wavelength, it means that the energy of your wave has actually changed. So it's as if the light was just getting tired and losing energy. And that energy actually goes, conservation of energy is still true. It's just that the interaction between the energy of that wave and the energy of space-time itself is what you need to consider. You need to consider the whole system. But the net result is that when the light, by the time the light reaches us, it's redder than it was when it started.
Right, which is what I was going after in the original bringing.
Yes,
up,
but
right?
it's not
So
because not because
of that effect, but similar conceptually, right, to that effect.
Yeah, but it's not because the object is receding from us.
Right.
It is, but that's not what counts here. Both objects could actually be stationary. Light gets emitted, and then they start to move away. You would still observe the phenomenon.
Yeah.
And then from that difference in frequency that you observe, and we know that there is a difference in frequency because those stars emit very specific wavelengths, right, because of their composition. So we know how to recognize, okay, that's helium, and it should be at this wavelength, and it's at this one instead. So we know by how much it was shifted.
Right.
And we can even infer data about any clouds of gas that it went through on its way. And here is where it's really interesting because so you have that light that is traveling for billions of years, and at some point it encounters a cloud of gas. So that cloud is going to absorb some of that light. So that's going to make holes in the spectrum. So you're going to be able to infer the gas composition of that cloud and so on. Okay. But wait, you have a second cloud of gas a little farther away. But by the time it reaches that second cloud, the universe has expanded, right? So in the end, you're going to observe those holes in the spectrum, but at different wavelengths, because the wavelength of the light has changed between the two.
Okay.
And we actually do observe that.
Oh, that's interesting.
But in the end, what counts is that from that redshift, we can inject that into cosmological models and get the distance from that. But this is getting trickier and trickier because we need to know more and more things here. We need to know the Hubble parameter. We need to know the amount of matter and dark energy in the universe, which are things that are also not easy to measure.
Right.
So it means that those distances are, they depend on that, and so the uncertainties also depend on that. So here the uncertainties can be up to 20%. But 20% still gives you a good ballpark estimate of those distances. So we know that this galaxy is about 10 billion light years away. Yeah, so that's pretty much how we measure distances in the universe.
A few different ways to do
it.
Pretty cool.
Yeah, and we started with objects in the solar system. Those distances are fairly easy to determine by just looking at the position of these objects because they are not that far. So we can plot their trajectories, and from Newton's laws, we can infer a lot of things.
Right.
And,
yeah, we have a good handle on what's in the neighborhood anyway.
Yeah, and another thing is that we can. Now we have probes. We can actually, go to those places, and we send radio signals from those probes, and we can measure how much time that takes, and so on. So the distances in the solar system are known very, very precisely. For example, the Earth-Moon distance is nowadays is measured by sending a laser beam to the moon.
I was going to say, for the moon, we just shoot a beam up there.
Yes, yes.
Now we're shooting beams to the laser.
Yes, and there is an amazing episode of Mythbusters where they actually they show that.
Yep.
So there is this laser station where you can shoot a laser to the moon, and when we landed on the moon, we put a special type of mirror there which is it's mirrors that are made of 3 mirrors at right angles that have the property that they just send back the light in exactly the direction that it came in.
Yep.
So there is one of those mirrors that is on the surface of the moon. And when you shoot anywhere on the moon except at this place, you see just, ordinary, you see nothing in particular because your light gets bounced everywhere. But
Right.
if you shoot at the landing site precisely, then you get a signal back.
Right.
You get your light back.
This always, anytime this comes up, it reminds me of the Archimedes death ray.
Yeah.
I feel like we should have one of these on the moon.
Which Mythbusters also tested.
Also on Mythbusters. That's a fantastic episode.
Yeah, they're great.
Yeah,
so
about that without thinking of that.
So yeah, for the moon, it's very easy. You just shoot a laser there, a very powerful laser because it has to go through the atmosphere, and you just shoot a pulse of light, and a little less than 2 seconds later
Right.
comes back. You measure how much time it took, and you can determine the distance to the moon with an amazing precision. Like
I can't imagine we're not already doing this with other planets and objects in our solar system from the moon. Probably are.
No, I don't think we are, but it would be interesting to drop one of those mirrors somewhere on Mars or
Something like that.
Yeah.
Curiosity needs a friend.
Yeah, poor little
A death
robot.
ray or a friend.
Yeah, we need to shoot lasers at him.
Who doesn't like shooting lasers at things, though? I mean, come on.
Yeah. On sharks and. Yeah, so we started with distances and ended with
lasers.
with freaking laser beams, as we should. So. Yeah. Okay, well.
All right. I think that's it.
Yep, I think it is. Cool. So this has been another episode of Absolute Zero.
Until
I'm
next
Bertrand,
week.
and we'll see
we're
you
out.
next week. Bye.